So section 1 was patterns, section 2 was arithmetic sequences, and now we're doing geometric sequences. And actually, we've been seeing geometric sequences already in this chapter. You just didn't call them geometric sequences yet. So to get started, let's find the fifth term in each of these three sequences right here, and then talk about how these sequences are being generated. So for part A, what would the next number be? 3, 6, 12, 24, 48. And for part B, what would the next one be? Okay, and then for part C, what would the next one be? Positive or negative? Positive, 1 over 243. So what's happening each time in all three of these? They have something in common. Multiplying by 2 in the top one. Okay, what about the middle one? But division is actually multiplication of the reciprocal. So actually they're all using multiplication to generate the next term. And like I said, we've seen a few of those, like from section 1. We had situations where we were multiplying to create the next term. And that's what's going on here. In this one, we're multiplying by 2 each time. We start with 3, times 2 is 6, times 2 is 12, times 2, and so on. On this one, we're starting with 0.1, which is 1/10, by the way. And then we're multiplying by 1/10 to get 1 100th, 1 1,000th, 1 10,000th, 1 100,000th. On this one, we start with 1/3, and we're multiplying each time by what? 1/3. But actually, it's negative, because that's a negative 1/9, that's a positive 1/27, that's a negative 1/81. So we're actually multiplying by negative 1/3 each time, so that the sign keeps switching from positive to negative. That's a geometric sequence. If you multiply by the same amount each time, rather than adding or subtracting by the same amount each time, then you're dealing with a geometric sequence. And that's what this whole section is about. So, geometric sequences are built by multiplying each term by a constant. That constant that you're multiplying each term by each time is called a common ratio. And we use the letter R for common ratio. The ratio of one term and the previous term. If I take one term and I divide it by the term before it, and I reduce that fraction down, that gives me the common ratio. Now in the last section we had the arithmetic mean. In this section we have the geometric mean. The geometric mean of two numbers, A and B, is, I take A and B and multiply them together, and then I take the square root. The arithmetic mean of two numbers was I take the two numbers and add them together, and then I divide by 2. Here we're taking the two numbers and multiplying them together, and then taking the square root. And finally, the important thing for this entire section is right here. The explicit definition for a geometric sequence is a sub n, which we've seen from the previous section, equals a sub 1, which we know, times r to the n minus 1. And we've seen that to the n minus 1 before. On the homework, there were several problems that asked you to generate the formula for it, and in the answer we had an exponent with a variable minus 1. So, this is your term n, again, whatever the actual number is for that term. This is your first term, again. But this is called the common ratio. And then this n right here is still the term number. And again, the common ratio is found by taking a sub n and dividing it by a sub n minus 1. So you're just taking one term and dividing it by the term before. So if you had the second term, you could divide it by the first term to get the common ratio. All right, so just like the last section, we have 3 examples here. Let's see if these are geometric sequences, and if they are, we'll write the equation for it. 3, 6, 12, 24, 48. Is that a geometric sequence? Yes. The reason that I know that it is because if I take 6 and divide it by 3, I get a common ratio of 2. If I take 12 and divide it by 6, I get 2. If I take 24 and divide it by 12, I get 2. If I take 48 and divide it by 24, I get 2, which means that there is a common ratio here, and it is r equals 2. That's an r. The only other thing we need is the first term in the sequence, which we have. A sub 1 equals 3. And now we can write the equation for this geometric sequence. It's going to be a sub n equals a sub 1 times r to the n minus 1. Just substitute in what you know. A sub n equals 3 times r, which is 2, to the n minus 1 power. That's your equation. Now it's worth noting that order of operations tells me that I have to do exponents before I can multiply. So can I turn this into a 6? No. I have to leave this alone. This has to happen before this, and since I can't do this with that variable sitting there, I can't do anything with combining here. I can't multiply that out. It's got to stay just like that. How about the second one? Is this a geometric sequence? By the way, this answer was yes, it's a geometric sequence. This one is not a geometric sequence, to answer the question. But what kind of sequence is it? It's actually an arithmetic sequence because we have a common difference. Each time we are adding 3, plus 3, plus 3, plus 3. So even though this says, no, it's not a geometric sequence, so technically we don't have to write the formula for it, we are going to write the equation for this guy. What's it going to be? Yep, we're writing the formula for an arithmetic sequence. We already know everything we need to know, so we have a sub n equals what? N minus 1, and then we prefer to put that in like slope-intercept form. So then we distribute a sub n equals 3 plus 3n minus 3, and then we get a sub n equals 3n. Actually, we saw that one in the last section. We didn't have to do that here, but it's worth seeing again just for the extra practice. Okay, how about that third one? To decide if it's a geometric sequence, what do we have to do? Look to see if there's a common ratio. So that means we need to take one term and divide it by the term before it. So if I take 3 to the 10th divided by 3 to the 5th, what do I get? Yeah, 3 to the 5th. If I take 3 to the 15th divided by 3 to the 10th, what do I get? 3 to the 5th. If I take 3 to the 20th divided by 3 to the 15th, what do I get? Because when I'm dividing like bases, what do I do with my exponents? And I keep the base. So I get 3 to the 5th. What is 3 to the 5th then? I don't want the number. Tell me what it is. What vocab word is that? It's the common ratio. So this is a geometric sequence. 3 to the 5th is the common ratio, r. Is that a better looking r for you this time? So my answer here is actually yes. And then I need to write the equation. Multiplying? It's easier to figure out if there's a ratio. The word ratio implies division. If you divide this term by this term. So now I know that there is a common ratio. It is a ratio. And we're going to write our equation, which will be what? equals A1, which is 3 to the 5th, times the common ratio, which is 3 to the 5th, to the n minus 1. So, is that our answer? Yes? This is going to be n minus 1 no matter what we do. I do want you to simplify those exponents. So I need to know what 3 to the 5th power is. Three times 3 times 3 times 3 times 3 is 243. So this becomes a sub n equals 243 times 243 to the n minus 1. There's your answer. It shouldn't be very surprising to you that this is what we get, big numbers like that, considering the sequence was already 243 to begin with, and then multiplying by 243 each time. The reason why these formulas work is the first term in the sequence is 3. To get the first term in the sequence, I need to plug 1 in for n. If I plug 1 in for n right here, I wind up with 1 minus 1 in my exponent, which gives me 0. And then anything to the 0 power is 1. So 1 times something better give me that first term. So that something better be the first term. So this little notation right here is backing us up 1 term. In doing so, it decreases the exponent by 1. But then basically we're multiplying by that first term. And that's exactly what's happening over here as well. So that's sort of like the concept behind why there's an n minus 1. And if you did the homework from sections 1 and 2, you saw this a couple of times. Now you know why. Those were actually geometric sequences that you were seeing. So carrying on. Find the 10th term of the geometric sequence 4, 12, 36. I know everything I need to know here. Actually, I didn't even need that third term, because I've told you that it's a geometric sequence. Because it's a geometric sequence, what do I know? There must be a common ratio. And in this case, the common ratio is going to be what? Because 12 divided by 4 is 3. Or you could go 36 divided by 12, which is also 3. It's always one term divided by the term before it. So the common ratio is 3, which means now what can I do? Yep, you can write the equation, which will be perfect. And so that's the equation. This problem is not asking for the equation, though. It's asking for the 10th term. So what do? Plug in 10. A sub 10 equals 4 times 3 to the 10 minus 1. So what do we have to do first? We have to do the exponent first. So we have 10 minus 1, which is 9. So 3 to the 9th. A sub 10 equals 4 times 3 to the 9th power. You're probably entering that into your calculator. What do we get? 1683? But then times 4. 78,000 what? 732. There's your answer. So not a whole lot of work. You just got to understand how the geometric sequence works and then remember the formula. Yeah. You read those? Nice. Okay, what are the second and third terms of the geometric sequence 2 something something negative 54? Very good. It is going to be a negative common ratio. Because of this negative number right here, my negative common ratio is going to be a positive times a negative to give me a negative, and then a negative times a negative to give me a positive, and then a positive times a negative to give me a negative. So I know that my common ratio must be negative. In addition to that, my numbers here are getting larger. So I know that my common ratio must be bigger than 1. Because I'm multiplying by a number each time, not by a fraction. So, all that aside, to do these problems, remember what we did with the arithmetic sequences when you had missing terms. What do we know in this problem right now? We know the first term, which is 2. What else do we know? We know the fourth term. A sub 4 equals negative 54. And we know it's a geometric sequence. So we're going to have a sub 4, that's right, equals a sub 1, which is 2, times r. We don't know r, that's what we need to find, to the n minus 1. N is 4 right now. So 4 minus 1. Well, what is a sub 4? It's negative 54 from over here. So I can say equals negative 54. Basically what I'm doing is I'm substituting in negative 54 for a sub 4 right here. So now this is what I'm looking at. All I got to do is solve for r, and we know how to do that. We have 2r to the third equals negative 54. Solve for r. Divide both sides by 2. R to the third equals negative 27. So what number times itself 3 times gives you negative 27? Negative 3, yeah. We would take the cube root of both sides, and the cube root of negative 27 is negative 3. So r equals negative 3, which is exactly what we kind of thought without knowing the actual number before we even went into the problem. We knew it had to be negative, and we knew it had to be bigger than 1 because our numbers here were growing. So let's check to see if we have the right answer. 2, and then the next term will have to be what? Negative 6. And then the next term will be positive 18. And then what is 18 times negative 3? It's negative 54. So the answer to this problem is negative 6 and 18. If it asked you for the common ratio, your answer would be r equals negative 3. Okay, can we do the same thing with this one? Yes, we can. Or there's a faster way. Geometric mean, that's right. Just like with the arithmetic mean being the average between the two numbers, and that would give you the middle number. So if this was an arithmetic sequence, you could just average the two numbers and then find that middle number. With a geometric sequence, you can use the arithmetic mean to find that middle number. It only works if there's only one number there. And it only works if it's a geometric sequence. But the geometric mean is the square root of these two numbers right here being multiplied together. 3 times 12 is the square root of 36, which is 6. That's the middle number. What am I multiplying by each time here? 2. 2. Okay, physics problem. Physics is just the kind of the study of how things occur around us. It's not scary. So when you see that word physics, it's just like something that can happen naturally in our own class if we wanted to. When you bounce a ball, the height of consecutive bounces forms a geometric sequence, just like the picture that you see here. You've probably noticed that before. Each time the ball bounces, it bounces a little bit less high each time. So it's telling you that this ball bounces in a format that makes a geometric sequence if you were to measure the height each time after it bounces. What are the heights of the fourth and fifth bounces? Could we take the geometric mean of these two numbers? That would give us this. And then we could figure out the ratio, sure. The better way to do it would be a little bit shorter, I think, to do what we did, not the last problem with the geometric mean, but the problem before it where we had some missing terms and we were trying to generate the common ratio. Because I did tell you, or the problem does tell you, that it forms a geometric sequence. So that means we know we have a common ratio, and right now we know what? What's this one? The first term. And what's this one? The third term. So it's just a real world problem, but it's exactly the same thing as we've been doing. So let's go ahead and do that. We know that a sub 1 equals 100, and we know that a sub what? 3 equals 49. We need to actually generate the equation this time. In the last problem we didn't have to do that, so that's why using the geometric mean was fine. But this time we need the common ratio. So what do I write? A sub 3 equals 100. Three minus 1, that's right. And what is a sub 3? 49. Equals 49. Okay, so let's simplify that. We still have the 100, what? R squared equals 49. Now what? Divide both sides by 100. And we get R squared equals 49 over 100. And don't start feeling queasy. What do? Square root both sides. R equals 7/10. Yeah, those are both perfect squares, so this is easy to do. Now, technically, if we took the square root of both sides of an equation, we should include plus or minus. But in this case, because of the fact that we are always bouncing positive, if we were to say that we could have an R that was a negative number, that would be like it bounces and then it goes below the ground and then it comes above the ground and then it goes below the ground. So the negative in this case doesn't count, doesn't make sense. So just positive 7/10 is the correct common ratio. So now what do we do? Write out the equation, which is what? A sub n equals okay, now let's answer the question. What are the heights of the fourth and fifth bounces? So a sub 4 equals 100 times 7/10 to the 4 minus 1. Just type it into your calculator. 100 times 7 divided by 10 to the third power. Still? Give me a decimal. What is it? 34.3. Okay, and then a sub 5, same way. You've already entered in a sub 4, so all you got to do is go up and change your exponent. 100 times 7/10 to the 5 minus 1 this time. And what do we get? $24.01? You think so? That's what you got? What did you get? No, we're on the fourth and fifth. This is the second right here, right? Yeah, so 24.01. All right, we'll see. So there you go. That's how you handle that. Once you get the common ratio, you can write the equation fairly easily. And then from there, calculate whatever bounce number they want. Okay, down at the bottom it says use your equation and your calculator to iterate more bounces. How high will the ball go on the 10th bounce? Well, we can use the equation to figure out the 10th bounce pretty easily. That's just going to be a sub 10 equals 100 times 7 over 10 to the 10 minus 1. And we have that already entered into our calculator, so we can get an answer pretty quickly. What do we get? 4.04. And what are the units on these, by the way? Centimeters. So all of our answers should include centimeters. We don't want to leave that off. So we might get mistaken and think it's in inches or something like that. And then if you work for NASA, that equates to crashing billions of dollars worth of equipment into the surface of Mars and then losing your job. Is that what I did? Yeah, that's what I did. No, actually, that's what convinced me that I shouldn't work for NASA. Yes. So let me clear all those off of there. And we're going to use the calculator to set up an iteration here to do this for us. This common ratio, the common ratio of a geometric sequence, tells me that every single time I want to generate the next term, I have to multiply by the common ratio. Just like the common difference in an arithmetic sequence tells me that I need to add or subtract by the common difference. Here I'm going to multiply by the common ratio. So to set up this iteration, I'm going to type in 100 and press enter so that my answer is stored. Why am I using 100? That's my first bounce. That's my first term. And now I'm going to multiply by the common ratio to get my next term. My common ratio is 7/10. So 7 divided by 10 and press enter. And there you go. The second bounce actually went up 70 centimeters. And now because I'm using my answer, my previous answer, I can go ahead and hit enter again, and I get my third bounce, 49 centimeters. Hit enter again, I get my fourth bounce. It didn't give me a decimal though. Hit enter again, I get my fifth bounce, sixth bounce, seventh bounce. So now I have all of these exact. If you don't like that, then start over. 100 and put in a decimal point. Enter. Oops. 100. Why is it doing that? That's weird. And then put in a decimal point and then hit enter. And then multiply times 7 divided by 10. Hit enter. And then hit enter. And then hit enter. And now it's giving you the decimal. Hit enter, hit enter, 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 enter. And there is my 10th bounce. If I want to keep going, I can keep going. Am I ever going to stop bouncing according to this equation? No. Because forever I can just keep doing that. Eventually I get to a point, though, where it'll stop. And that's due to friction and air resistance and stuff like that. So the real world has more than just stuff like this going on. But if there was no air and there was no friction, then this thing would actually continue bouncing for forever. Not space. If we were in a vacuum with no friction, like on a skating rink. A vacuum. And this bounce was perfectly elastic, meaning that no energy was lost in the bounce. In order for that to happen, you wouldn't be able to hear, feel, or see anything, which is never going to happen. So eventually enough energy will be lost to where this ball stops bouncing. And that's physics. So back to the geometric mean. The geometric mean of two positive numbers A and B, why do they have to be positive? You can't take the square root of a negative number, that's right. So they both have to be positive, and then I multiply them together, and then I take the square root, and that gives me the geometric mean. Since both numbers are positive, the geometric mean is positive. To find the geometric mean, multiply the two numbers together, take the square root. So what am I going to do here? Square root 64, which is 8. That 8 fits directly in between these two numbers if it's a geometric sequence. 2 times what gives me 8? And then 8 times what gives me 32? So if it's a geometric sequence, You found that middle number. You can use the geometric mean to help find missing terms in a geometric sequence, as I've already shown you. If you do, you need to consider positive and negative cases. In other words, it could be geometric mean or its opposite. So what are the possible values of the missing term in this geometric sequence? To do this, we have to take the two numbers and do what? Multiply them together. And then take the square root. Well, what's 48 times 3? So we have 144 being square rooted, which gives us 12. But because this is a geometric sequence, we have to include the plus or minus. Because if I have the positive 12, obviously 48 divided by 4, 48 times 1/4 is 12, and then 12 times 1/4 is 3. But in the negative case, 48 times 1/4 but negative gives me negative 12, and then 12, negative 12 times negative 4 gives me back to positive 3. So both of these numbers actually work. So you have to say both, which means that the answer is actually C.